Okay, hello, welcome everyone to another seminar in computer engineering. It's our second seminar in this second semester of 2024. Good afternoon over here in Brazil. Good night over there in India, right, where our distinguished lecturer is based. Today we have the pleasure of having a great distinguished lecture on a very hot topic, this concept of general intelligence, this artificial general intelligence. It's the main topic that Professor Alex James has been working and will provide the insights on what is the current state of the art or the next frontier. How is hardware evolving to support AI? Okay, very hot topics these days. As usual, Alex, I don't spend our valuable time in reading this large bio. Everyone can check online, and so I invite you also to visit Alex's websites, his recent publications. Okay, and with that, Alex, I will stop sharing and thank you for accepting the invitation. And I pass you the floor is yours. Let's
Yeah.
talk again in around 40 minutes. I have some questions from the students, from the live chat over YouTube as well. They are welcome to put questions. Thank you.
Wonderful. Thank you, Christian, for that. I'll share my slide and directly get into it so that we leave enough time for the questions.
Okay.
Yeah. So let me share. I hope that's visible.
Okay. Yeah, something is coming. Yeah, we are
All
seeing
right.
your screen. Thanks, Alex.
So what I will do is through this talk, I'll uh, kind of introduce at a higher level like what AGI and AGI chips are, and then give some directions in which like the field it's going from a hardware perspective. So I'll keep it as simplistic as possible in terms of the the concepts and so on and so forth. So if there are some questions, please do feel uh, free to ask as we go by. So two terms which are very popular when we think about AGI. One is the performance, another is the generality. So what performance means in general, when we think about performance, we are talking about like accuracy of a system, or we are looking at like the ability of that function, functional level ability to see that AI is performing as good as humans in a particular task or the other. Now that can be quantified in terms of certain matrices or statistics and so on and so forth to benchmark and compare between humans and machines. Now, in terms of hardware, this performance also means a few other things. You are also looking at whether things like energy efficiency or like the reliability of the system and so on and so forth also comes in. So there is performance is rather like when you have both the software and hardware, both of these performance means two different things, and this both of these needs to be taken into account when building a system. The second part is relatively bit harder. How do you make the system general enough? Suppose you have a particular algorithm or a particular like neural network or something that is used to build that AI system. And now, can the same system which is trained to work in a speech recognition task, will that be able to work equally good in a face recognition task and so on and so forth? Can you reuse the same thing, or how general enough is the system so that it becomes trainable and retrainable and reusable on multiple different tasks? Now, you might have seen this before, like being able to use like AI for example, creating a game. Um, like in this example, like the entire game can be created the rules and everything can be generated out, the graphics can be created. Likewise, you would have also seen like recent videos that have come out, completely generated uh, using generative AI. Now the problem when you see is like these uh, images look very very real. They're completely generated. Now why is it that like not everyone is using it now? By this time, like we would have thought like, oh, we should be able to generate all sort of videos to everything in a very realistic way just by giving a set of prompts. One of the reason why this is challenging is because of the hardware limitations that is there. So every time when you do a prompt, we are using large number of GPUs to process that and generate those, whether it's images or whether it's videos. Now, the energy that is required for generating those are no way comparable to how we could think about like human level intelligence. Brain would consume maybe 20 watts, whereas like the present day computers would, the best of the parallel processing computers and chipsets, everything put together, we're looking at like kilowatts to megawatts of power for an equivalent task to be run. So energy is a major bottleneck. Um, the complexity of how much you need in terms of hardware is another task as well. While you can see your brain is so compact and you being able to do like so many different tasks and it's general enough, the same is not true when it comes to like present day computing systems. Uh, there are several practical applications one can think of. Like this is another example where the news reader or like the sports commentary can be completely translated. So there are plenty of applications one can think of, but in all of these cases, we are looking at like the need for a lot of hardware to make it work. This is another example. OpenAI had come up with MuseNet, like generating like music and so on and so forth. So extending and pushing the idea from one particular task to another task and so on and so forth. That kind of tells like gives you a sense of like early form of what could be an AGI. As we go further, we'll see that while GPT kind of systems are really something that you can see, but they are still like far away from what a general intelligence, a fully functional human level intelligence would be. So what is AGI? In a simple terms, we are looking at like bridging towards a natural intelligence like humans. So being able to understand, learn, and apply intelligence across a wide range of tasks. And we are comparing that to the human cognitive ability. So when we are talking AGI, we are saying we are somehow being able to map the same kind of like capabilities as that of a human level. Now, there are three different aspects to that AGI when you compare to the current systems, large number of systems, which we call as like weak AI or narrow AI. So narrow AI is very specific, or weak AI as we know it, like is very specific. It works really well in certain tasks, but the same system when you try to use it in another task, it doesn't work, or it doesn't work as good as it should. So a whole lot of like examples one can list. Now obviously like artificial general intelligence should be just opposite to that, like where we are trying to make the system such that the scope is broad enough, it's capable of wide range of tasks, whereas at the same time it's adaptable as well. So if there is a situation where it put in an unknown situation, it should be able to adapt, learn, relearn, and be able to perform the task. Whereas weak AI requires very specific programming for each of the tasks, while adaptable nature of AGI means like that kind of like specific training may not be required. Like it kind of learns from all the different environment and tasks that it is familiar. The third part is the autonomy that comes in. The level of autonomy what we expect in an AGI is equal to like how much a human will be able to autonomically make a decision. Now, weak AI lacks this capability completely. Many a times, a human would need to uh, initiate that task to make that algorithm run or do a particular task in a particular way. When we talk about autonomy, that is just the opposite. Like just like how humans would make a decision of, say, taking a right or taking a left, the algorithm will be able to make a judgment based on the context, based on the situation, and so on and so forth. And one can think of various components of AGI. The key part one would be the learning and adaptation. So being able to learn from a diverse set of data, experiences, and to adapt to new situations and challenges is one of the core aspects that we look at when we think about an AGI system. The second part is like understanding complex concepts and making those decisions, even if the information presented to is incomplete or ambiguous. Another important part we will see is the natural language or ability to understand languages. And in fact, like if you look at the AI literature, a large part of intelligence was attributed to that fact that like the machines would be able to communicate like and have a question answer system or reasoning and these kind of things was seen as like one of the ways in which this intelligence could be achieved. Next part is the perception. So if you look at the perception, we had a lot of different sensory data that comes in, and how what do you do with that? How to understand that environment? Many a times, like if you look at today's like AI algorithms, um, a collective multi fusion kind of like algorithms are not usually present, which would help like understand the environment fully. And if you start collecting a large number of data from the sensors, the amount of data that one needs to process also increases significantly. That means again, all of these tasks requires like huge computing resources of the hardware to go along with. The last part is often debated, the self-awareness and consciousness. In some of the theories, you would see like it's strongly argued that self-awareness or consciousness is part of it, whereas like the certain other literature or like understanding would be that you don't really need to have it because we as humans like we don't really use it on a day-to-day task, but it may be present, but directly we may not be using. So there is arguments around it whether you really need it or not. So if you think about AGI system, possibly like there are many ways to go about it. One is symbolic AI. This is the early AI systems which were primarily all focusing on symbolic rule-based systems. Then we have machine learning and deep learning. If we are able to mimic like large neural networks, similar to neural networks in the brain, by giving a large amount of data, taking into account all the different possibilities over many years of data collection and so on and so forth. Now, the size of these networks could be enormous to compete with like what the brain would be doing, and even the algorithms we are assuming to be very similar to brain may not be exactly doing the justice to how the brain itself is doing it. So that's where the third thing comes in, to look at like the brain itself more carefully, looking at the cognitive architectures and trying to make sense of can we mimic some of these and find a purpose to it. The fourth could be a combination of many of these things together. So if we use a combination of symbolic with machine learning or like cognitive architecture and try to see whether it can efficiently mimic some of the properties of the brain like as we know it. Fifth, again, is another interesting approach where one could think of evolutionary route, where the natural selection of evolution to solve the problem could be used. Algorithms could build algorithms, or neural networks that could build neural networks. AI which could build AI and improve itself, so that like eventually it reaches the same capability of that brain without a human intervention in the process. So multiple ways. And one thing you can add to this also is the uh, advances that are happening in brain computer interfaces and so on and so forth. Can you actually complement what is there in the brain with the algorithms and the machines that which are the data that comes from the machines. Can they both be combined to create such systems as well? But of course, it comes with a lot of challenges. Computation complexity in terms of like implementing it in hardware is a challenge. Generalization ability across different domains and tasks is going to be one of the major issues. When you have like a lot of data, when you have a lot of information, then safety and control also becomes an important factor. So if the AIs are not able to be regulated and controlled, then we would not know like how they are going to behave in the future. So giving the right kind of data would be one way to control it, but then there are many ways in which it could also find a way not to obey those rules which humans are setting. Other aspect is ethical and moral considerations which can come into this, including the autonomy, decision making, the societal impacts it may have, the way the humans would think about the morality and the ethics may not be the same way in which the algorithms could evolve. So that can lead to some conflicts if you're trying to create a society which would have both of these. Fifth could be a bit challenging of how the consciousness itself would evolve over the years, and how the AGI would would mimic it. The one question is whether do you really need it, and the other part is like if you are going to have it, then what form it will take, and so on and so forth. The last part is data and privacy concerns around it. So especially when we are handling like large amount of data sets, um, and because there are multiple different tasks it could be used, you're having access to multiple different types of data. So a person may be using this data. So the data could be something like your hotel reservations to your banking statements to you drinking a coffee. All those things may come into picture, and that may directly, even if you don't give the name of the person, the algorithms may be able to figure out whether they are it's this person or not. So data and privacy concerns could be other aspect that come into. In terms of hardware requirements for AGI, we are looking at like starting from a high performance computing, which is what we use largely these days in terms of CPUs, GPUs, and TPUs. Along with this, because we are using large amount of data, the storage becomes like again an important part. How quickly you can access the data, how large the storage space itself would be, and so on and so forth becomes critical. Now, this model is relatively very hard to scale, because as you have like more and more amount of data, training them as a whole consumes like huge amount of hardware. That's why like over the last decade or so, people have been really rethinking that model and thinking about why not do computing at the edge, why not do chip level solutions for accelerating those AI algorithms rather than having general purpose like processors for doing it. And that's where AI accelerators, neuromorphic chips come into play, where we are looking at more efficient neural network processing. Now, once you have that, the next stage would be to decentralize the whole processing, distribute the computation load onto these processes, which are extremely low power compared to taking a server, and potentially like further integrating it to like parallel systems like quantum computing and others as it gets better and better, and the issues around like implementations get sorted. Now, just to get a more a philosophical approach of what are these levels of AI that we are talking about, we can divide it into multiple levels. The first we could say when there is no AI at all. So, looking at both sides, like the narrow AI and as well as the general AI or the AGI. An example of narrow level approach is maybe a calculator, or a general level approach would be a mechanical trunk. Now, if you are looking at emerging, say, level one, where the AI is somewhat better than unskilled human, so you could see some examples of narrow AI, emerging narrow AI, simple rule-based systems. Whereas emerging AGI, you can say ChatGPT or Brad or others like what we have today, LLM models, rather fit as like, it's still not very skilled level outputs that you get. You'd get like somewhat like unskilled output, and then you probably have to fine tune it. And maybe this will get better over the years, maybe slightly become better than unskilled. Now, if it become competent, we say it's at least 50th percentile of skilled adults. And today, if you look at narrow AI, there are several systems which could be compared at that level, like a Siri or Alexa, or IBM Watson. Could be considered as something that is like about 50% of a skilled adult. Now, if you compare it with AGI, such systems don't exist as of now. If you push it further, like call it experts, today you would see Grammarly, which would more or less like 90th percent of skilled adults. It meets that expectation. AGI, of course, there is nothing there. Um, and if it is reaching that 99th percentile of skilled adults, we can call them as virtuoso. Narrow AI, some examples are Deep Blue. Grandmasters find it quite challenging. So very few people are able to like compete with it. Now, what if a complete outperformance? Do we have something like that? We do have AlphaFold and others which are definitely performing better than humans at that. And of course, from the AGI perspective, there is nothing yet which surpasses the human abilities here. Now, along with this, we also need to look at autonomy, because that's also going to define the way like the AGI systems will be used. So if I see that from a hardware perspective, we are at a stage of AI 1.0 where we are looking at like AI chips. And when we are moving from that to say AI 2.0 or the AGI chips, obviously the complexity will be more, but then the applications will be even more as well. Now, pushing it further, a collective AGI where the multiple AGIs could be used in chiplet forms, kind of broad idea, or maybe in a network form or in a distributed form, they're able to communicate and so on. And the next level most likely is going to be where we are able to collectively use the biological intelligence as well as like the chip level intelligence to go together to create like something much bigger than the human intelligence itself. So some kind of roadmap where you could think like autonomy could be at various levels as well. So if you define that like say level zero, there is no AI, human does everything. So plenty of examples of it, like you're drawing something or sketching something with pencil and paper, or your non-AI digital workflows like text editor and so on and so forth. If you go to level one, we're using AI chips. So in this case, like humans fully control tasks and uses the AI to automate mundane subtasks. So example, like if you want to have a placement and routing for the chips. Now these days we have like many algorithms, including AI algorithms, which are used for doing this. So if you're going to put that on an AI chip, it's going to be very, very fast, like millions and billions of transistors gets connected in no time, in a very efficient way. But the thing is, it's still controlled by the humans, like the entire process is initiated by the humans. Now, if you go to the next stage where we are using AGI chips, the AI soon start to take like substantial role, but still to a large extent, like the humans control it. If you're trying to accelerate a chat GPT, a large number of like GPUs are used today to actually simply to give that performance that we are seeing in when you are doing a prompt. You're able to see the response to be very very fast, immediate generation and things like this, inference or tasks that are happening is very fast. So that kind of thing, it's possible because there is uh, a large number of like hardware that is actually going into it. Now the third part doesn't exist, but like we can think about certain possibilities, like where AI works collaboratively by but again it's invoked by the humans, but they work collaboratively. Now this could be some kind of distributed systems. We are looking at like very efficient communication to happen. The energy efficiency should be really good. If this were to happen, learning will be very much distributed. It's not going to be a centralized distribution. If it has to maintain like a very high energy efficiency and so on and so forth. The next level would be humans don't invoke the AI, but instead like it's autonomous completely, because it would be like human intelligence is part of that entire equation. So if you have like multiple connected systems now, can one brain communicate to another brain through those communication links through AGIs or multiple AGI chips and so on and so forth? Bit futuristic, but not impossible to imagine that that could happen. If we are pushing those boundaries, and there is a good chance that we may end up like creating such systems where multiple of those systems work together. There is like all sort of like federated like learning to many other things happening there. Now the next level could be if the AGI is going to just build like AGI chips or like things or general intelligence on its own, where there is no need for humans anymore, and this kind of like hardware itself starts to like control like everything. So for example, imagine a robot which would have like such a AGI like collective chips which are able to think about like how humans are thinking. Then we are looking at like the limitations of the machines that were there in terms of physical limitation, other things to be completely over, and it's able to replace the battery on its own, or the fuels what it needs to survive on its own will be able to repair its own. It will be able to fix things, it will be able to be creative, it will be able to program all sort of things that humans would do. It will be also able to do. Now, in the landscape of hardware, we are looking at AI chips of two forms. One is going in the accelerator direction, and other is the general purpose AI direction. And within that, in the accelerators, you can see digital only solutions as well as mixed signal solution, where you have analog and digital to come together. And also the different neural networks that you're familiar with, they are all implemented today. In terms of general purpose AI is still an evolving area. People are attempting, people are trying. In digital only, like LLM models and others have been tried out. I'll show a couple of examples of that. And mixed signal, again, like this is an area that we are my group is also like looking into like how to do that and explore those kind of things. So this is a interesting example. Like if you see LLM, like it's a wafer scale implementation of an LLM. You can see the size of it. Like if you try to put a billions of parameters into it. The target that this startup company is trying to do is, Cerebras is trying to do is to push the limits, like all these different LLM models, they're trying to put that in digital hardware. So most of it is digital. I am not sure whether they have tried like analog yet, but most of it, as far as I understood, it is digital. Another attempt of a similar thing is like Taikichi chip, like where the photonics based chips, like where they are trying out to use photonics idea to have like large number of neurons to go in. And then again, one of the demonstrable solution is, can we put like LLMs and things like this into this chips? So this was again like an interesting area. Like one could look into like how do you use like photonics and related things onto a chip, make it like energy efficient, communication to be very fast, store in multiple different ways. Like can you think about analog storage? Can you think about um, uh, lossless kind of processing and things like this, and keep the power very low. This was another one, Tinjik. It's a multi-core chip, which was initially, like, I remember this came out in news as saying AGI chip and things like this. The idea here is you have multiple blocks, like if you see down below, it's a multicast recurrent system kind of approach where you have like large number of cores, and the idea is like you could do multiple different tasks, similar to how your AGI idea is that like a system would be general enough to do multiple tasks. So conceptually, it's good. Again, the challenge would be to scale it up to very, very similar problems as how brain would compute. That's where the push is. So these are some of the practical efforts that is happening. Now, if you look at qualifying a technology, whether this is really possible or not, we ask certain questions like, is it something that you can fabricate? Can you integrate with existing CMOS foundry? Like, if you can't do that, like it is going to take like a decade or more before it sees the light of the day. Another is the technology scalable and is it affordable to the end user? If it is not, then it becomes commercially very difficult to compete in that market. So is it competitive to the existing technology? So there are a lot of very well established like hardware technologies out there. So whatever the new technology that we are bringing in, is it able to adapt very quickly, and go to like a large scale production? Now, these are challenging. This is where like the major bottleneck is. Although a large number of like ideas come out, like the question, from an industry perspective, it comes down to some of these things. Does it really make sense to have those kind of investment? What is practical today is still like CMOS, SRAM, DRAM. Other things that are coming up is memristors, photonics-based solution, and maybe some of the molecular and organic has been thought of, but that may take a lot more years to really come to the point where the comfort of CMOS and other technologies are presently at. So in terms of foundry support, you would see today like you have CMOS, SRAM, DRAM, and memristors in the in some of the foundries being tried. Like they're available as IPs. You can use it to build chips. Now, the memristors, of course, is very interesting, but then it also needs a lot of um, still things to do to make it completely mature, to be production ready and go it in large scale. So there are examples of what you can do with it, but then to be fully production qualified, it still is an emerging tech that is currently being tested out. Photonics again has a lot of potential, very real things. The cost of it, the ease of fabricating that into something really useful is the question. We are competing with CMOS, so can it completely replace that? At this stage, probably not. But is it possible? Probably yes. As we go ahead. So I work largely on some of the hardware systems related to memristors, algorithms, and others. So I'll just give a very quick tour of it. Given the time, I'll try to keep it like in another 10 minutes. So I'll just rush if something is not clear. Like just bear with me. So here, the idea of a memristor, the concept wise, is that it's able to link between charge and the linkage flux, and it gives a nice little concept of a device which could have multiple resistance state. So a single device which could be programmed to different resistive states, and to keep it in that state. So if you're able to retain that state, then it behaves more like a non-volatile device, or you can say a memory which would have resistors, analog memory which would have resistor. And you can model that using like state equations, and study the behavior, all sort of different complexity. And Professor Leon Chua from University of California, Berkeley was the first one to propose early Um, Late 60s and early 70s is where the whole uh, thing formally came into the literature. Now, what are the challenges? So we wrote together one tutorial. If you want to have a quick tour of, like, what are the variability challenges and things like this about these Memristive arrays that one can create and create like neural networks, so you can read that. So challenges you would have in these emerging devices is that variability will be there, and all sort of different devices behave and show some of those characteristics, like PCM, RAMs, and STRAMs, etc. And many different models are also there, which can be used to simulate this, analyze. Things like aging and reliability, read and stabilities, all those things become like an important factor when you consider the hardware for a long period of time. Certain variabilities come into play, like conductance drift, conductance change, noise, and interface electronics for these devices are also a very interesting topic of study. So whole sort of variabilities are there in non-ideal conditions when you build these chips, and energy is one of the key things we look at. So we have failures of the device happening, non-idealities, and all those things. In this, like, how does it perform? So just to give you a sense of it, neural network architecture itself is fairly tolerant to some of those variations. So if you look at 10% variation to a 40 percentage in something like MNIST, you would see not much of a change. But then if you reduce the number of levels, you can see there is a huge change in the accuracy. So number of levels become very critical because we are now talking about not digital level computing, we are talking about analog level computing. So what does it mean? So if you think about this as an array, and each of these are memristive device, each having a conductance value, so we can say that is conductance G, and the inputs X are fed as pulses or like signals through the rows. Then each of the columns, what you get is a current, which is a summation, weighted summation of input and the conductance. Now, this weighted summation is something that you would see is very common to a single neuron model. But then when you go to different neural networks, so which means like you are able to mimic that weighted summation or dot product operation for multiple neurons in a single crossbar. So here we have like 5 neurons represented in this crossbar. And if you try to build like circuits with this, you would see like
Let's see. There seems to be some connectivity issue with James. Can you hear me? Can the students hear me?
I can
Yeah,
hear you.
We do hear you,
yeah,
Professor.
yeah, I
Thanks.
can hear you.
Let's wait a little bit. Let's see if James is able to make it. In the meantime, let me share with all of you the questions that you have collected for James. They are very good ones. I've already picked a couple of them. I will share them also over YouTube for the other. There are too many to copy. Let me break this down in a couple of messages. Yeah, good work with the questions. So, how can I open these tips? In the Google chat, there's not so much space for questions. Let's see. As usual, the ethical ones on artificial intelligence, so the ethical challenges, something also James has commented about, especially in these scenarios where these autonomous scenarios, right, where the chips could be building their next generation of chips, right?
Hello?
Hello. Yes, James, I was.
Did I lost because I didn't.
You were in the slide where there was this 3D memory design.
Oh, okay. Then okay. So
And I was sharing already with the students many of the good questions that they have collected. So
okay.
if you want to move to the conclusions, and then we chat a little bit because they are very good ones.
Yeah, okay. So I'll just run through the slide.
Mhm.
I'll not talk about it. I'll just run through it.
Okay,
Um,
that's
yeah.
fine.
So, okay. Let me. I didn't realize that I went through a few more slides.
Okay.
Okay, no problem. Uh, I think this is where it was, right?
Yes, right.
Okay.
Before you
So
switch.
here, yeah. So here, the concept is this: like if you have each of those columns, like you could translate that each of the column, you can imagine it as like a neuron. So which means like if you have an array like this, then that can be a single layer neural network. So a single layer neural network could be translated to something like this as a crossbar array. And you can in fact go and build like the backpropagation algorithm as well into it. Then all sort of different networks. So and some way to compensate for the variation is by building something like a super resolution crossbar where we can connect like the rows. And what it does is like it will help you with creating large number of states with very few number of states. So just connecting like 7 or 8 layers, one can create like analog memories, and it follows very interesting like maths. You can actually check this out, this paper. It was published on the 50th birthday of Memristive in TKS1, where example of this is shown, and where if you use that, even with variability and even with like a few number of states per device, you can achieve like large number of conductive states, very much like an analog compute. and you can achieve similar accuracy as that of software. And you can build all sort of networks like LSTM, HTM networks. This HTM networks with face recognition example. Then these are generative networks which were built all on chip. So GAN and Pixel CNN. Pixel CNN was difficult to train compared to GAN, but it's fairly, like, in terms of hardware speed, like it will be much faster than running it on a server. Then another thing one could do is to mimic some of these things in quantum combining, like quantum circuits. The only challenge when you do quantum today is the errors that come by. Otherwise, from a algorithm simulation, we found that it was giving much better performance. But as and when the quantum errors come in, it becomes like challenge. One of the other thing one could do is also automate that AI design, chip design itself. So having like multi-objective optimization to find the right kind of hardware. And in fact, like once you take the hardware into account, your architecture also changes. So one here, like we have one set of combination when it's an ideal network. When you take non-idealities, then you have a completely different kind of network that gets formed. And especially when designing chips, then you would have to consider both the software and the hardware related aspects. So it becomes a multi-objective optimization to solve. You could try this out. We released one particular like tool where people can just, it's a GUI where you could just go and play with like different types of networks, see the hardware, how it performs, and how the algorithms compare with the software. You can select the device models and all those things and just simulate it. So these are some of the things one could do, aging analysis to that. And further, like you can also build like various different kind of configurations network to improve the number of levels, or in fact, like keep having like few number of devices. How can you achieve like more number of states and make it very accurate analog compute? And that can have like multiple application, like modular neural network, image processing. This is another example where you can use it for complete mimicking all sort of different filters, like all the convolution related operations could be mimicked from Gaussian, bilateral, Laplacian. All those filters could be implemented with these networks like this. The variability can be also effectively used in certain networks like echo state networks, where the first part of the network ESN layer is anyway like randomized and labeled, and then you have the dense layer to process. And these are some of the practical applications you can build with that. And some of the chip design structure that we look at is something like this, where you put in various different cores into a single chip, and then try to see how to make it like be able to perform like multiple tasks very efficiently. And there are of course like many challenges here in terms of energy efficiency and so on and so forth. Some of these are listed in this work. It's a short paper that was written, and a lengthier one is coming out soon. So where the major barriers and things like this in this field is listed. One final thing, there is a new journal like TCAS AI, and it basically focuses on most of these kind of topics where we have hardware and the software coming in. So and many works are coming into it, and I encourage you to read that. And at the same time, like if you are working in this area, to submit like works to this. We also have like one program called Maker Chips, where if anyone wants to learn some of these things from scratch, you could be part of it. Like it's 3-4 months of learning, where like we use open source tools and others to build the entire chip. So that's primarily that. Okay.
That's
Thank
great,
you.
James. Thanks. Lots of content, very exciting area, very multidisciplinary, right? Let me get one question that hits precisely this Make Chips initiative. One of the questions that that appeared from the students, and that is a logical one, is who are the main players today in these AGI chips? Are those already playing in the GPUs and smart NICs and all these well-established chip makers, or do you see opportunities for startups coming with new designs protected with intellectual property and eventually becoming a new player in, let's say, 10, 15, 20 years? I know it's very hard to guess the future, but how do you say the odds of the well-established against new appearing ones? Because there seems to be many breakthrough opportunities, right?
Yeah, very much so. So the thing is, like, when we think about AI or AGI, the way it is going, a lot of progress has been made from an algorithmic point of view. But then when many of these algorithms were built, the hardware was never thought of. So uh, because the, because it was not thought of, the hardware never thought of the algorithm as well, uh, what it will be used for. So NVIDIA is a very good example. It's very popular. It was never built for AI. It was built for gaming and things like this. And um, definitely it found an application because of matrix computation and others that was happening.
Mm-hmm.
Now, the challenge is that when we are thinking about the general intelligence, we don't have a full understanding of how it is working in the brain, right? So our complete understanding of the general intelligence is not there. So what we are building is always a guesswork. And we are trying to see. So even if the best companies in the world tries to put all the money, they are not able to mimic it fully, simply because we still don't understand it fully. So there is a lot of opportunities for startups in this space, because it's a high risk uh, proposition. Companies which are established are not going to put that kind of money and time and energy,
Mm-hmm.
because they need profit to sustain. They can't afford to fail. If they are having a business, they want to keep that business going. So it's very unlikely that they will leave aside like all those and then start looking at something else completely.
Mm-hmm.
And this is where the startups have a great opportunity, because they can think fresh. They don't have the baggage or limitations that a typical like established company would have. um, and today what is happening is, many of these ideas that startup come up, at some point in time the large companies would like to have a look at it and maybe acquire it, rather than them self starting it.
Mm-hmm.
So,
Yeah, yeah.
yeah, so I think largely it's a field with plenty of opportunities for the startups, whether it's devices, whether it's the kind of architectures that one needs to build, the hardware software co-design methods that one needs to have, even the memories, like where the data needs to be efficiently stored, coming up with those kind of memories which are fast, efficient, suitable for AI processing. All those things are opportunities out there.
Right. Yeah, yeah. Good, good. Yeah, yeah. That was my feeling, that this is an interesting space for startups. You pointed very well. Those well established are not likely to put money into a business that may kill their current business. Let me dig into one of the areas that you commented is a very promising one, because I have many colleagues in the faculty working on photonics. Why is it that you think with photonics there are interesting physical properties? Maybe those also related or explored in quantum. I don't know. It's not my my field. That can be reused and show a lot of potential. Why is photonics so hot as a candidate enabling technology or approach?
Yeah. So one thing is like photonic speed. You cannot compete the speed of light.
Mm-hmm.
Um, Another is the losses, and the whole thing you can, because you can do it in analog, means like many of those operations which typically we find it hard, like say someone wants to do multiplication, or someone wants to do things like Fourier transform, and all these kind of things can be much more efficiently done with light.
Mm-hmm.
So the only problem is how do you generate it, right? So the source is a problem. How do you feed the light? How do you take it out, and so on and so forth? It's kind of a bit challenge. They're
Store,
not
right? How do you make a memory, right? A loop.
memory. Exactly, exactly. So there are some bottlenecks like that, which makes it a bit hard. But then maybe the answer is not that a full uh, complete photonics chip. Maybe a part of it can be
Mhm.
photonics, and part of it will be the traditional chip. That could be the way to go about, especially if we are going to scale it down to 2 nanometer, and we are going pushing it further. Then having to reduce like any kind of and it could be something that could be used. People have been trying neuromorphic like neural networks with photonics, so that is also a very interesting area. If it can be scaled down into like multiple chips and so on and so forth, it is going to really compress like the energy and all those things. That's
Yeah,
nice.
nice. I think you have a point then, that maybe the end design it will be a system. Like at the end, our bodies are systems of systems, right? And then a subsystem of the memory could be with one
Exactly.
technology, the main processors or end co-processors of different types. Yeah, yeah. A hybrid of hybrids, right?
Yeah.
Yeah. Last
Exactly.
last topic I like very much. There are many things that I learned in your lecture. The virtuoso and superhuman level 4 and level 5 levels, which I didn't know
Right.
that was a term. And what would be your shot? When would you think that there will be a AGI technology autonomously improving itself? Are we talking about 10, 20, 30? What would be your shot in terms of years that will reach some of this level 4 or even 5? Another hard one.
Yeah. I think like the biggest challenge there is not reaching the last step. I think usually what happens is when these things intelligence
That
scale.
will reach some of this level 4 or even
Exactly.
5.
Exactly. So
Another hard one.
yeah. I think like the biggest challenge there is not reaching the last step. I think usually what happens is when these things intelligence
That
scale.
will reach some of this level 4
Exactly.
or even 5.
Exactly. So
Another
hello.
hard one. I think we got
Yeah.
into a loop.
Hello. Yeah, I think so. There's some
You have
loop going on.
also the YouTube streaming over there. Can you
No,
check?
no, no. What happens is these things intelligence
That
scale.
will reach some of this level 4
Exactly.
or even 5.
Nothing from my side.
Another. Maybe it was one of our students with the mic. Ah, okay, I think I got this. Okay, looks like James is again down. Uh, and it was one of the mics probably of the students that entered into our system. Okay, I know it's. Let me say bye to James. James, Hello. I think we narrowed it down to some microphone with some delay of the YouTube streaming, making it into our own stream. Okay. And it's 2 p.m. over here in Brazil, so the classes are starting. Many of the students need to leave, probably into physical in-person classes. And with that, I would like to thank you again for the great content. Congrats also for this new publication. Looking forward to look into it. And thank you again, James. Keep safe.
Thank you.
Probably into physical. Bye bye.